It is well known that non-hermitian quantum mechanics can provide a description of dissipative system in a minimalist fashion. It has gained attention recently due to the rapid progress in experimental implementation of non-hermiticity as a photonic experiment and cold atoms, where it has been revealed that the non-hermiticity changes the properties of a number of well-known quantum phenomena, were explained in the Hermitian physics, ranging from quantum topological phase transition to quantum magnetism. The mode that we consider is given by the Hamiltonian, where the imaginary I have the imaginary kinetic energy given by the first time and the potential interaction U. The number of sites and particles are N and M respectively. The Hamiltonian above can describe a 1D homogeneous ring system in which IT imaginary kinetic energy strength is given by this equation. Moreover, have the which subspaces labeled by a wave a key which the moment index in the subspace. I get the spatial relations given by this equation, where for the negative potential interaction, we have the lowest energy of the bound pair is equal negative U on subspace K is equal P. Furthermore, the bound pair state is given by these equations, where gamma parameter is given by this equation. Quantum entanglement. The quantum entanglement is the quantum mechanical property that Schrödinger singled out many years ago as the characteristic trait of quantum mechanics and has been many analyzed in connection with Bell inequality. A pure pair of quantum system called entanglement with it is infactorable in convey a mixed state is entangled if it cannot be represented as a mixture of factorable pure state. It is a well-known fact that the quantum information theory can be used to get condensed matter physics characterisms of quantum phase transition that are characterized by the ground state energy of quantum many-particle system. Thus, the quantifying of quantum correlation in this many-body system enhances condensed matter physics quantum information theory. In Figure 1, I get the behavior of von Neumann entropy of reduced density matrix, where I obtain the divergence of the von Neumann entropy in the limit of zero temperature. As expected, this is the large rising of quantum fluctuation in this limit. I get the decreasing of the von Neumann entropy in the range of high temperature. I obtained a very small difference for different values of potential interaction U represented for different color in the figure, and I have the parent Hermitian system can be obtained by assuming complex IT by a real T. For the Hermitian system, the bond pair with the law of energy lies in the key is equal to zero subspace, while the ground state energy of a two-particle non-Hermitian is equal to zero. The definition of von Neumann entropy is of a density matrix rho is defined by the formula S is the trace of rho logarithm rho. I have the ground state of the composite system. The Hilbert space is defined by this equation, It does for the Schmidt decomposition procedure, we can write the eigenstate of composite system given by this equation. Consequently, I have the entropy, von Neumann entropy, then the two partitions of the system defined by this equation. In the figure 2, I get the behavior the von Neumann entropy as a function of potential interaction U, where I obtain the minimum of the von Neumann entropy near to the point of 3.5 for the potential interaction. And after that, the entropy starts to rise. I studied the entanglement, another quantum entanglement quantified that given by the entanglement negativity. This is defined by the equation 2. I have the negativity given by the formula, and furthermore, I define the logarithmic negativity, the negativity of the entanglement. I make the analytical calculation, obtain the expression for the entanglement negativity given by this equation 4, where this is the partition function of the system. In figure 3, I get the behavior of entanglement negativity as a function of temperature for the Hubbard model for different values of potential interaction and for a complex hoping T. I obtain the negative in terms of a rise with temperature for all values of complex hoping in this case. As a conclusion, we analyze the quantum correlation and entanglement in the non-hermitian Hubbard model. In general, the effect of Magni split on quantum correlation in the non-hermitian Hubbard model is a complex problem that requires detailed analysis. It's worth noting that the field of non-Hermitian quantum physics is relatively new and is still under active research. Therefore, the specific details and implications of magnetic splitting in the non-Hermitian Hubbard model may vary depending on the specific system. The partition considered in which the local entropy is calculated is infinite. We get a strong variation of the entanglement with the non-Hermitian coupling parameter. In a general way, in a quantum species, the real field or complex field generates a split of the generated ground state, where the spins are aligned along the direction of the external magnetic field. However, the eigenvector of the system with which we are expecting will not suffer many changes with the external magnetic field, and the initial state displays oscillating behaving periodic among all possible spin configurations. Thank you very much for your attention.